Okay, welcome back. I think fixed whatever the heck was going on before. So what I'm trying to do is motivate why we're using the particular rules of SD that we're doing, or that we're actually using. And so we're familiar with the rules that we have, right? All the introduction and the elimination rules of conjunction, disjunction. So we have conjunction. This is the way we've sometimes been writing it in class. Then we also have disjunction. We have negation. We have the material conditional, and then we also have the biconditional, which we're still going to do a brief lesson on in just a little bit in another video. And we have introduction and elimination rules for all of these guys, right? So there's two different kinds of rules that we have for each of these connectives. And there's other rules that we noticed that we could actually introduce, and we talked about this briefly towards the end of the video, where we had something like, if you had so if these are meta variables, if you had a sentence like A and B, then why couldn't you actually just do B and A, based on the fact that these actually are truth functionally equivalent, right? So this would be valid inference. And you would be right to point that out, that this is a rule that we could introduce. But why aren't we introducing this in SD? And one reason why is because we want to be a little bit minimalistic about which kinds of rules we introduce. In other words, we want to keep things as simple as possible and see whether or not we can get all of the other kinds of inference rules from the very basic ones we want to do. In other words, if you're at all into some of the mathematics, for example, you want to see how much work you can do with the minimal amount of operations as possible. Or if you think about certain games, the idea is, you can sometimes make, in a board game, for example, you can sometimes make new rules that, given that you can see certain moves ahead, you might want to say, I want to introduce a faster rule to get to that goal state. But in most of these games, you actually have these sort of rules that only allow you to make sort of one step at a time. So if you think about two people playing chess, for example, they might both have particular kinds of moves that they play at the beginning, and so you might think, well, let's just jump ahead to that position in the board game. But in fact, you need to take turns and play one move at a time for each of your players. And similarly, this is what we're going to be doing here. So let me say a little bit about where we're kind of headed with this. So here's an interesting question you should keep in mind, is do you think if you had just the rule of the biconditional, do you think you could express any sentence using just the biconditional that you could express using the combination of these connectives? Or think about it like this, suppose you just had conjunction here. Do you think you could use just conjunction to be able to even express a sentence like not P or Q? And it turns out that you can't do that. In other words, conjunction is not expressive enough to be able to capture all the things that can be said with each of these different connectives. But it turns out that you can actually do that with just negation and disjunction. In other words, anything that you can express with the combination of all of these, you actually just need two of these connectives to be able to express all of those. And we're going to cover that a little bit later on in the course. But the reason why I want to bring it up now is because it turns out we can do a similar thing for a system SD. In other words, we could actually get an inference like this one that we're doing over here just by using some of the poor rules that we've been doing, that we've been using up till now, right? So the idea is we could actually prove this inference using just the rules that we have so far. And so the idea here is a sort of minimalistic project. We want to figure out what are the least amount of rules that we need to be able to do all these big inferences. And so after we've proven to ourselves that you can actually get these kinds of inferences, at that point we then we'll let ourselves do these sort of faster rules of replacement. And actually, maybe it's a good exercise to actually prove that this is the case, given that the rules that we have. So let me do that as an exercise, just sort of off the cuff. So we're going to assume for a particular case, and this is actually important. So before this was a schema, right? That had to do with meta variables. What we want to show in this case is, suppose you have the sentence A or B, right? Our goal is going to derive B and A. Now, notice we're doing this for a particular sentence, right? So the schema, that's talking about an infinite number of different sentences, right? Any kind of conjunction, you can swap the two conjuncts. In this case, we're just doing this with a particular sentence. And it's relatively easy to get to this, right? We first use conjunction elimination from line 1. This will be line 2. And then we can use conjunction elimination again to get B. Oh yeah, I should put elimination here. And that'll be again from line 1. And then we can use our rule of conjunction introduction from lines 2 and 3. And when we bring them together, we're saying, you know, the order in which you bring them together doesn't actually matter. So this is from lines 2 and 3. And in a way, actually, the fact that we said the order in which these things appear in the derivation, the order there, because the order there doesn't matter, you can introduce like this, is in a way sort of implicitly building in the fact that addition is called commutative. But notice that we've done this just for a particular sentence. We haven't proved this for every conjunction, right? And the fact that, although we see this intuitively and it seems very obvious to us, that is something that we actually need to prove. We need to prove that for any two sentences, P and Q, their conjunction, you can swap them, right? That it's commutative. And this will be the kind of property that we end up proving when we get to systems that are a little bit more complex, which we call SD+. So right now we're sort of working in just a minimalistic system because we want to figure out what are the sort of simplest rules based on the connectives that we have to be able to derive the things that we want to derive. So hopefully that provides you with a little bit more motivation for why we're picking the rules that we are, even though they might seem a little bit arbitrary at first. But sort of retrospectively, when we get to some of the features later on in the book, you'll see a little bit more why we ended up picking those ones that we did.